K01 Relay Logic Control. Relays as devices are covered in Module D. However, a quick review of the basics is appropriate here. An electromechanical relay, or EMR, is a device that uses electromagnetic forces to close or open switch contacts. In other words, an electrically powered switch. This is a sketch of a concept of a relay. If you made your own, it may look like this, but in reality, you would buy an off-the-shelf relay that looks more like this or these. Relay contacts come in two basic configurations. Normally open contacts, or NO, which are open in the unenergized state and close when the relay coil is energized. And normally closed contacts, or NC, which are closed in the unenergized state and open when the relay is energized. By convention, the relay symbol always shows the contacts in the unenergized state. Relays are available with a variety of multiple contact configurations, two of which are shown here. A double pole, double throw DP-DT relay, a triple pole, double throw 3P-DT relay. Both would probably come in a package that looked like this. No doubt, relays were first developed to satisfy two electrical control needs: remote control, the ability to turn devices on and off from a remote location, and power amplification. An example of power amplification is the starting relay in a car. A low current ignition switch energizes a relay, which in turn passes a high current to the starting motor. Electrical designers soon recognized that relays could be used to implement control logic, and, or, and NOT gates, as well as flip-flops can be wired from relays. For the AND relay, A and B must be energized for a voltage to be at X. When a voltage is applied to coil A, it causes the switch contact to move from open to close. The same for relay B. Remember, the drawings show the switches when the relay coils are not energized. For an OR gate, if either relay A or B is energized, the output X receives a voltage. For a NOT gate, if relay A is energized, the output is 0 volts. If it is not energized, the output receives a voltage. A flip-flop can be made from a relay using a principle called sealing. Once the relay is energized, an electrical path through the contacts takes over the job of providing power to the coil, and the original A voltage can be removed. This process is frequently called latching. To unseal the relay, the power coming through the contacts must be temporarily removed. Remember, the drawings show the switches when the relay coils are not energized. Switches and relays became widely used in industry for controlling motors, machines, and processes. A switch can turn a single machine on and off, but a relay logic network can control an entire process, turning on one machine, waiting till the operation is done, then turning on the next operation. Decisions can be made by the logic. For example, if a part is too tall, it goes in one bin. Otherwise, it goes into the other bin. Eventually, the ladder diagram, a special type of wiring diagram, was developed for relay and switching control circuits. This drawing shows a ladder diagram. Notice it resembles a ladder. The ladder diagram consists of two power rails, which are placed vertically on each side of the diagram, and rungs, which are placed horizontally between the power rails. The power rails are the source of the power in the circuit, either AC or DC, where the left rail is the hot side and the right rail is the neutral or ground if it's DC. Therefore, each rung is connected across the voltage source and is an independent circuit. A rung typically contains at least one set of switch or relay contacts, and usually only one load, such as a relay coil or motor. When the contacts in a particular rung close to make a continuous path, then that rung becomes active and its load is energized. For example, the top rung, shown here, contains two switches and a pilot light in series. For the rung to become active, both switches must close, which will then apply voltage to the light. The middle rung has two switches in parallel, so only one of those switches must be closed to make the rung active. The load in this rung is a relay coil, relay A. The bottom rung contains a set of normally open contacts from relay A, and the load is a motor. Consequently, when either SW3 or SW4 of the middle rung closes, a relay A coil is energized and the motor in the bottom rung starts. Many control situations require that a time delay be inserted at some point in the process. For example, a mixing operation might take 90 seconds, or a conveyor belt might be allowed 10 seconds to reach speed before parts are placed on it. A relay control system would use a time delay relay to create the time delay. Once activated, the time delay relay will wait a predetermined period of time before the contacts open or close. The delay may range from less than a second to minutes. Time delay relays are categorized as either on delay or off delay and are best explained by example. A 5-second on delay relay with normally open contacts will wait 5 seconds after being energized before closing its contacts. When the relay is de-energized, the contacts will open immediately. An application of the on-delay function is a security system that delays activation for a period of time after being turned on to allow the occupants time to leave. The off-delay relay provides a time delay when the coil is de-energized. For example, a 5-second off delay with normally open contacts will close its contacts immediately when energized. When it is de-energized, however, the contacts would remain closed for 5 more seconds before opening. An application of the off-delay function is car lights that remain on for a period of time after being turned off to provide light for the occupants as they leave the vehicle. Note the symbols used for time delay relays, specifically the arrow types on the arms. Timers have both normally open and normally closed contacts, so you can make or break contacts. The ones shown here are normally open. They are open till energized, then they close. A small electric furnace has 2 heating elements that are energized in 3 stages, 3 minutes apart. That is, when the furnace is turned on, the first heating element comes on right away and the second element comes on 3 minutes later. A temperature sensor will shut down the furnace if it gets too hot. Draw the ladder diagram for the control circuit. We start with our power rails. On the top rung of the ladder diagram, a push-button switch energizes the heater relay, and the relay is sealed by the H1 contacts. This action supplies power to the first heating element, element 1, via the relay contacts H2, and energizes the TMDY delay relay, the on-delay relay type. After 3 minutes, the time delay relay activates the second heating element via the TMDY1 contacts, bottom rung. At any time, if the stop button is pushed or the overtemp sensor contact opens, the seal is broken and the heater relay de-energizes, causing both heating elements to shut down. Note that power is removed from both relays and the normally open contacts return to their open state and power is removed from the heating elements. Also note that if the temperature got too high and the elements were turned off, when the temperature drops, the elements won't be energized until the operator pushes the start button again. How would you change the circuit to automatically start up again? Would you need another temperature sensor? Could you use another timer? Several different designs for delay timers, which use different operating principles, have evolved over the years. In the past, pneumatic and thermal relays using bimetallic strips have been used to make timers. Solid-state time delay relays are used in most newer systems that require delay relays. These units are based on the delay involved when charging a capacitor, or more commonly counting high-speed clock pulses with a digital counter. The higher the count, the longer the delay. Some applications require the use of a counter instead of a timer, and the application is similar to the timer just discussed.